Welcome to the Explainer. Okay, we're jumping right in today because we're tackling the strict, unforgiving mathematics that dictate true aerial firefighting success. We're stripping away all those dramatic Hollywood visuals you usually see to look at the raw thermodynamics and the exact hard numbers required to actually extinguish a wildfire from the sky. It's literally a math problem, and we're going to solve it.
So, here is a roadmap for today's explainer. Number 1, the retardant reality check. 2, measuring fire energy output. 3, the physics of cooling. 4, calculating true coverage levels. And finally, 5, achieving total suppression success.
All right, let's start with Section 1, the retardant reality check, myth versus math. I want you to completely forget everything you've seen on the news or in the movies about those dramatic, bright red drops from airplanes, right? When we picture aerial firefighting, we typically picture giant air tankers dropping thousands of gallons of red fire retardant. But here's the critical, mathematical truth we have to face. Retardant drops are indirect. They're designed to coat fuels ahead of a fire, not put the fire out directly. Because of this, they actually have an effective BTU cooling capacity of exactly 0. Yeah, literally 0. If you want direct suppression, if we actually want to kill the flames, you need massive energy absorption. And for that, we absolutely have to use calculated drops using water and enhanced water polymers.
Moving right into Section 2, measuring fire energy output. Think of this as the lethal checkbook.
We are going to treat this fire just like a lethal checkbook that we absolutely must balance. If the fire is writing checks in heat, our aircraft must deposit enough cooling capacity to cover those checks, or the fire wins. Simple as that. To do this, we have to know exactly how much physical space our aircraft is interacting with every single second. Step 1. We take an air tanker flying at, say, 160 knots and convert that speed to feet per second. That gives us 270.1 feet per second. Step 2. We look at our fire. Let's assume it has a rate of spread of 100 chains per hour. When we convert that, it gives us an active fire width of 1.833 feet per second. Step 3, we just multiply that length by the width. 270.1 times 1.833 equals 495.1 square feet. What this means is that every single second, our aircraft is interacting with just over 495 square feet of active burning fire line.
So the crucial question here is, how much heat is actually inside that space? Well, if we look at a standard fuel model for fire, one with, say, 4% dead fuel moisture and 125% live moisture, it is generating a staggering 2,700 BTUs of heat per square foot. That's a massive amount of energy.
When we take that massive heat generation, that 2,700 BTUs, and multiply it by the 495.1 square feet our aircraft covers every second, we start to really see the true scale of our enemy. Over 1.33 million BTUs of energy are being generated every single second. To put that into perspective, that is the exact debt in our thermal checkbook that we have to pay off, second by second.
Okay, on to Section 3, the physics of cooling, thermodynamics in action.
Now that we know the fire's ridiculous energy output, let's figure out how we actually go about absorbing all that heat. It's not as simple as just dumping a bucket of water, because water's cooling power actually changes based on where you are geographically. So you might be wondering, how does altitude change water's power?
Let's break this down methodically. You know that as you go higher in elevation, the boiling point of water drops, right? Let's assume our fire is raging at an altitude of 4,736 feet above sea level. Through our altitude factor calculations, the boiling temperature of water up here drops from 212 degrees down to 203.2 degrees Fahrenheit. Now, if our water starts at an ambient 48 degrees, bringing it to a boil absorbs 155.2 BTUs per pound. That's what we call our specific heat. But the real magic, the heavy lifting, happens during the latent heat of vaporization, the energy it takes to actually turn that boiling water into steam. That phase change absorbs a massive 970.3 BTUs per pound.
If we add those two numbers together, we get our total thermal capacity, 1,125.5 BTUs absorbed for every single pound of water dropped. And since a standard gallon of water weighs 8.34 pounds, a single gallon of fresh water at this altitude can absorb over 9,380 BTUs. Now we finally know the exact value of the deposits we are making into our thermal checkbook.
This brings us to Section 4, calculating true coverage levels, closing the deficit.
Okay, we have the fire's energy output, we have the water's cooling power. Let's bring them both together. The mathematical bridge from gallons to BTUs is what we call the coverage level. It works like this. You start with the coverage level, which is really just a measure of gallons per 100 square feet. Then you convert those gallons into physical weight. And finally, you mathematically translate that directly into our BTU cooling capacity per square foot.
So what actually happens if we use a standard coverage level 6 drop? Well, as we just calculated, 6 gallons per 100 square feet equals 0.06 gallons per square foot. When we multiply that by the weight and our thermal capacity of water, it only gives us 561.9 BTUs of cooling per square foot. But wait, remember our fire from earlier? It was producing 2,700 BTUs per square foot. If we drop a standard coverage level 6, we are severely unmatched. Our drop is mathematically 4.8 times deficient. The check bounces. The fire simply evaporates that water, marches right forward, and the fire wins. No contest.
To actually match the fire's 2,700 BTUs, we mathematically require a coverage level of 28.8. That translates to 0.288 gallons per square foot. When we run the thermodynamics on that volume, it absorbs 2,697 BTUs, perfectly balancing the checkbook. But, and this is a big but, here's the catch. To deliver a coverage level of 28.8 over our calculated active area, the aircraft must drop an astonishing 142.7 gallons of cooling agent every single second.
Let's wrap it up with Section 5, Achieving Total Suppression Success, the 3 rules. Let's really cement how we apply these complex calculations out in the real world. The fundamental takeaway here is that you cannot fight a dynamic, moving fire using static measurements. It just doesn't work. To succeed, you must follow 3 golden rules. 1. Convert the aircraft speed to feet per second. 2. Convert the fire's rate of spread to feet per second. And 3. Convert the aircraft's drop rate to a per second metric. This is exactly how we match our aerial energy inputs directly to the fire's exact BTU output. We are syncing the timeline of the attack perfectly with the timeline of the fire.
But think about it. Delivering over 142 gallons of fluid per second straight into the heart of a 2,700 BTU fire requires absolute maximum efficiency so that the water doesn't just drift away on the wind or fail to penetrate the fuels. Therefore, to ensure direct suppression success and maximum energy absorption, these calculated water drops are highly recommended to be executed using enhanced water polymers. Remember, retardants give you 0 direct cooling, but polymers drastically improve the water's ability to blanket, stick to, and just suck the heat right out of those fuels. Which leaves us with this final critical thought. We have treated aerial firefighting like an art form for decades, right? We've been relying on indirect retardant lines and basically hoping for the best. But if we finally embrace the strict thermodynamics, if we rethink our aerial inputs to perfectly match a fire's exact energy output using calculated drops of water and enhanced polymers, how could this undeniable math change the future of wildfire survival? It's a powerful question, and honestly, the numbers speak for themselves. Thank you so much for joining me on this explainer, and keep learning.